Hello, everyone. Thanks for joining us today. Today we'll continue talking about collections, discuss several algorithms, and especially concurrent versions of collections. I remind you that you can ask all your questions in the chats. We will try to cover them all. And as always, if you like what we're doing, please press likes and subscribe to our channel. And without further hesitations, I'm passing the word to Luca.
Okay, so let's start. Can you hear me?
Yeah, everything is great.
Okay, so today we are going to complete the talk about Java collections. And as you can see from the agenda, we have been covering the first part up to the single pointer linked list. Today we are going to discuss another flavor of linked list, namely double pointer one. And then we are going to discuss operations and implementations related to stack, queue, hash map, hash set briefly. And finally, we are going to introduce concurrency and show how to cope with multi-threading when it comes to use collections. A brief recap of part one. What we have been doing is to introduce abstract data types as a way to specify, to define types for pieces of data. And we have been more interested in data that represent collections, such as a queue. If you remember the queue example of abstract data type. Then we discussed the data structures as representations of ADTs. So on the implementation side of an ADT, we have data structures. We show some differences among collections, namely ordered collections and unordered collections. Ordered collections, as an example, lists, and unordered collections, as an example, sets. Then we briefly discussed homogeneous and non-homogeneous data structures with a brief reference to Java generics. We show how to classify data structures in terms of their structure, actually. So linear data structures and non-linear data structures. If you remember, we saw an example of a search tree. And we have been discussing some operations that are quite common when it comes to use collections and generally speaking in data structures. And we have been talking about sorting and iteration over a collection. We also introduced the main classes and interfaces of the Java collection framework: the set, the list, the queue, the stack, and the map. And today we are going to discuss their implementation or example implementation. And okay, we also talked about some concrete data structure like arrays and linked list in a single pointer fashion. Okay, I have some clarification to give you related to some errors and some situation where I've been not being precise in during the first part. So the first point is related to the map interface. I've been talking about a collection when talking about the map interface, but the map interface does not specify a true collection. It does not extend the collection interface. However, this interface contains collection view operations which enable it to be manipulated as a collection. So it's a kind of in-between situation. And the second point is related to the warning which is raised when we instantiate a collection without using generics. And that warning, I said, was coming from the JVM. This is not precise. The warning comes from the compiler, and the compiler might not be considered as part of the Java virtual machine. And the interface providing the iterator method is called iterable and not iterator. And this is another point. And finally, the most important point is related to the question that has been asked during the QA session. And it was about a list and array comparison. And I said something like, we should prefer a list when the situation is dynamic, when we have a bunch of insertions and removals and things like that. This is basically correct in the sense that when we hit the end of an array, a dynamic array, the cost of insertion becomes linear. But the overall and the right way to actually analyze the situation is based on amortized cost analysis. And amortized cost analysis proves that the cost of insertion in a dynamic array is constant if we carefully choose the resizing strategy. So basically, it is true that in the very worst case, adding an element into a dynamic array has a linear cost, but in an amortized sense, this cost is actually constant. Okay, let's start the talk, let's say the content of the talk. And we start from a new flavor of linked list. You should be at least not completely new to linked list implementation, because in the first part we discussed the single pointer version. What happens now is that we add an object reference in the node of the list. You can see on the left part of the slide, and sorry, and you can see that we also keep a pointer to the tail of the list. And of course, it's not shown here, but in the nodes we also have data. You can see it in the class node shown up on the left. I will not go deep into showing you every possible situation when it comes to insertion and deletions of nodes. I will simply discuss insertion after a given node. And you can see that we have to perform some operations which are quite similar to what we have been doing in the single pointer case, namely the first two lines. So what we do when we insert into a list after a given node, say the predecessor, is to instantiate a new node, and then we actually set the next pointer of the new node to target the predecessor dot next node, which means the successor. And then we adjust the predecessor next node to target the new node. And this is quite similar to what we were doing with the single pointer linked list. Now, with the double pointer linked list, we have to take care also of the previous pointer to the previous node. And we adjust accordingly. The new node previous pointer is going to target the predecessor. And then the new node dot next, which is the successor, previous pointer, is going to target the new node. It's a bit kind of tricky, but it's not complicated. When you go to implement these kind of operations, you just need to take care of be careful on how you adjust pointers, but object references. About the operations themselves are not so complicated. And on the right, if you remember when we talked about the list interface, we had the iterator method that was returning an iterator object. And then we have specific to the list list interface, a list iterator method, which returns a list iterator object. This particular iterator is able to scan the list backward. And now you can understand how it is possible. So in the snippet of code, you can see how to scan the list backward. And basically, we can do that thanks to the presence of object references to previous nodes. Okay, so the stack is another data structure that it's quite common and it's widely used. In Java, the stack class extends the vector class. But keep in mind that in most cases, the DEQ interface should be used as stack. So this is a warning. It is still instructive and good to know about the stack class and how it works. But when it comes to use a stack in production, you should better use an implementation of the DEQ interface as stack. This is because extending vector, the stack class is not able to behave, let's say, as we would expect in some situation. So just keep this in mind. And the vector class is an implementation of a dynamic array. I already explained you how dynamic arrays work. And in fact, dynamic array can expand and shrink when it is required. And okay, also the other 2 points, we already have been through this also during errata coverage. Operations of insertions and removal in a vector do not have the same cost. In these cases, it is possible to use an amortized cost analysis. And let's discuss briefly a possible evolution of a stack. So moving left to right in the picture, we can see that if we start from an empty stack and we push, what will happen. So you remember that in a stack, we want to implement the last in, first out policy. So we push on top of the stack and we remove elements from the top of the stack. So we push and we pop. And so if we push an element, what we do is just adding the element into the vector, and we just keep track of the actual index of the top of the stack. So basically, we push and we increment the index. And similarly, we push another couple of elements, dog and pig, and these elements are added at the top of the stack. Then we pop and we basically return the pig element, which is on top of the stack, and we decrement the top index. So basically it works like this. And as you might observe, we don't remove the pig element from the stack. This is quite common in arrays. We don't have an actual let's say, hard removal of elements. When we remove nodes from a list, when we delete from a list, we just cut out the node, and the node will be garbage collected. In the case of arrays, we don't have this kind of removal operation. What we could do is to erase the content of the slot, but otherwise we can simply wait for the slot to be overwritten. The last point is related to overflow. If the top is greater than or equals to size, we might have a stack overflow. And in this case, it's not going to happen because the array is going to expand. So, but what is a stack overflow? It's a situation when we have basically no more spaces for elements in the stack. Okay, so this is an example algorithm, and I would like you to take a screenshot or a picture and go through it, read it, and maybe you can tell me what the algorithm is doing during the QA session. And then we might have a discussion about it, okay? I will give you a few seconds to take a screenshot and then I will move on, and during QA session we will get back to it. Okay, so we are talking about the queue now, and in Java, the queue interface is implemented by many classes. And there are some flavor of queue that implementations that are mainly related to multi-threaded programming. As an example, blocking queues are using concurrent programming, and they work as follows. If the queue is empty, we wait for an element to get in for a certain timeout, and in a similar fashion, if it is full, we wait for space. This is not, let's say, what we are going to discuss next. We will focus on the simplest implementation of a queue interface, which is the linked list. The linked list is not thread safe as a data structure. And a data structure is thread safe if can be used, and it provides countermeasures when it comes to multi-threaded programs. So if a data structure is to be used in a multi-threaded program, it must be thread safe, or it must adopt some kind of countermeasures. We will say something more about it later. So let's check out these pictures here, and we want to insert an element into the queue. And given that we have to implement the first in, first out policy, we have to insert at the end of the queue, and we have to retrieve elements from the head of the queue. So the end of the queue, the tail is on the left, the head is on the right. We are going to insert our element cat at the end of the queue. And how to do that is pretty much straightforward. We just instantiate a new node with the cat element inside. Then we set the next pointer of this new node to target the same object reference as the tail is referencing, namely dog. Then we adjust the previous pointer of this element, the dog element, to target our new node, the cat. And finally, we adjust the tail pointer in the list class to target the new tail of the list, of the queue. And when it comes to removals and to retrieve of elements from the queue, we perform something similar. So we just remove the head of the queue, and we adjust the head pointer in the list class to target the new head of the list, and we return the element, the first element. So first in, first out. Okay, this is probably the main topic of our talk today, and it is about hash functions. So given that we have to introduce an implementation of the map interface, which is called hash map, we need to know what a hash function is. And so a hash function associates a number to a piece of data. And the number associated with the data will be used as an array index. What does it mean? It means that we want to build a function. We would like to have a function such as that when we receive an element, as an example, to be stored into an array, we just compute the function over the data itself, and we automatically get the array index where to put the element. And it is not always the case when it comes to hash functions that we want to compute an array index. So in some other situation in computer science, you might find hash functions used for other goals. But in our case, we want to compute an array index. An example of hash function is modular hashing. And so if keys are positive integers, we might compute a hash function of key using the remainder operation. So given m, the size of the array, we just compute the remainder operation, key and m, and we get an array index. So the remainder operation is basically, I give you an example here on the right. You should be already familiar with it, but you can see that if the size of the array is m, the remainder operation, the result of the remainder operation over whatever index is going to be in between 0 and m minus 1. And these are all legal indexes for, and these are for an array of size m, and these are all the possible indexes of the array. And another example of modular hashing is for strings. And you can see an example code here on the left, on the lower side of the slide. And you can see that basically what happens is that we compose somehow the hash value with the numerical representation of the characters of the string. So we loop over the string and we combine the numerical values with the hash that we compute, also multiplying it by a small prime integer. And for our objects, so we have a solution for positive integers, we have a solution for strings. What happens, as an example, if I want to use my object as a key for the hash map? Right now, it's not completely clear, but the thing is, when we use custom objects as keys for a hash map, we have to make sure that the hash function, the hash code method of that object is well defined. So how could we do to define, what could we do to define such an hash code method? We could use the hash method of the objects class, which would combine the hash codes of the values attributes. And it would do that in a similar fashion as you can see for the strings. So it would combine them in a similar way. Now that we know how to compute, let's say, an index out of a piece of data, of a string as an example, let's see what happens. And what happens is that basically we can compute the index and insert into the array. But in some cases, even though given two keys, key 1 and key 2, and key 1 is different from key 2, we get something like the hash function returns the same value for the two keys. So we have a problem, we have a collision. So a collision is such that given two keys, two elements we want to store in the array, we get the same hash value. We will see in the next slide how to cope with this. I just want to tell you something about properties of hash functions. We talk about uniformity for a hash function when every output value is equally likely. So every index is equally likely, and it's the hash function does not, let's say, give birth to indexes in a biased way. But even in the case of a hash function providing a good performance in terms of uniformity, collisions are still possible. Why? Because it depends on the size of the array, actually. So basically, if we think about a huge amount of elements to be inserted, and we have a small array, the hash function is going to collide because of the reminder operation. So how to cope with this? Well, what happens is that in a hash map, so first of all, remember that in a hash map, we store key value pairs. And we store key value pairs, but we don't do that in a, let's say, naive way, because we have to cope with collisions. And to do that, we store, instead of storing just a key value pair, we store a node, as the one you can see on the top left corner. And you can observe, and you should recognize it, that this node is a node of a single pointer linked list. So what happens is that when there is a collision, when we experience a collision, we basically are going to use a linked list, single pointer linked list, to store the elements. In this way, we are basically solving the problem of collisions. So given a key value pair, we compute the hash of the key, we get an index, we go to the slot in the array, we find out the slot to be occupied, well, we add the slot to the head of the list, or to the list. Okay, this part, I already told you that HashMap requires good implementation of hash codes and equals method for keys. This is because these methods are used during operations. So if you use custom objects as keys for a hash map, make sure you have good implementations of hash code and equals method. Now we have solved the problem with collisions, but we do have another problem. Why? Because if the array size is not, let's say, appropriately chosen with respect to the amount of key value pairs we are storing, what we are going to get is a bunch of collisions, and the bunch of collisions are going to generate long lists. Now, long lists are going to take the data structure far from the performance we would like to have. So instead of having, as an example, when it comes to retrieve an element, instead of having a constant performance, we might have something much worse, because there is a long list to be scanned to find the actual element. And so we have solved the problem with collisions using lists, but we need to cope with performance problems. And the concepts I'm going to talk about now are related to this problem. So the first concept is initial capacity for a hash map, which is the number of initial slots for the array. And the default is 16. Not such a big array, actually. The load factor is the percentage of slots that have to be full before rehashing is triggered. What is rehashing? Rehashing is resizing the array, increasing it by exponentiation. Basically, we double the array size every time we perform rehashing. So what's the idea here is to avoid long lists, increasing the size of the array. But when we change the array in a hash map and we already have elements inside, we need to recompute the hashing and hash values for those elements, because if you remember the hash function, it includes the reminder operation, but the size of the array, which is part of the reminder operation we are using in the hash function, has changed now. So everything has changed, and we have to recompute the values for the hash, for the various elements, the hash values. Okay, let's briefly discuss the implementation of the set interface via the hash set. I will not talk about operations, just briefly related to this data structure. So hash set implements the set interface, and it is backed by a hash map. So we use a hash map to basically implement the set interface. And the elements in the set must not be duplicated. And this is because, if you remember, in the set interface would like to capture the mathematical concept of set. And we already said that the mathematical concept of set does not permit duplicates. And so what is done is a bit tricky. And what happens is that the elements are stored as keys. Note that are stored as keys, not as values, in the hash map. And this is going to guarantee uniqueness for these elements. So what happens, as an example, if you want to add the element cat to the set, is that we generate a somehow fake key value pair with the element itself on the key side of the pair and the dummy object on the value side of the pair. Now I wrote new object here. Actually, what would happen is that we would not generate different object for dummy objects. We would have a single object to save some space. But let's say, functionally speaking, it's this is what happens. And after generating the key value pair, we are going to put it in the hash map as usual, using the hash function, and we would be able to retrieve the element if and check for its presence using the functionalities of the hash map. Of course, there are other operations over sets like union, set difference, and things like this. You can check that out there, that implementation for those functions in the web or via books. Okay, the last topic we are going to talk about is concurrency. And more specifically, we would like to understand how to use data structures and collections in multi-threaded programs. But before we can do that, we need to understand the concurrency problem. So let's try to explain it. And let's assume, as an example, that we have a counter variable, integer counter, that we would like to increment in a multi-threaded program. So we would have something like two threads, thread A and thread B, that increment this counter. And the actual instructions that are to be executed when it comes to increment a counter, basically, it's not just an instruction. What would happen is that the counter would be read into a register. It would be summed, added a value, 1, to the content of the register, and then the new value, computed value, would be stored back into memory. And in an ideal situation, a thread A and thread B would execute these instructions, let's say, in a sequential way. But the actual truth is that the CPU is going to, and the operating system, most importantly, are going to schedule the threads on the CPU in an interleaved way. So basically, those instructions are going to be mixed somehow together, as you can see in the right of the slide. So let's try to understand what can happen. If you see during the execution of the write, on the right, thread A is trying to do his increment, to increment the counter, and thread B is trying to do the same. But thread B is going to read the counter before actually thread A updated it with the new value. So if you assume that the initial value for the counter is 0, we can read the various instructions and understand what happens. So thread A is reading into the register the value 0, summing 1 to the value 0. And it's in the register A, we have 1 now. Thread B is going to read the counter now, and it's going to read 0 itself. Now, thread A is going to store back the value into the counter variable, and the value of the counter will be 1. And then thread B is going to execute its last 2 instructions, and it's going to sum 1 to 0, and we get 1. And then we write back. Thread B is going to write back into the counter the value 1. So at the end, in the counter we have a value which is 1 when we would have expected the value of 2. And the reason for this is that this execution, interleaved execution, is not, let's say, equivalent to a sequential execution. And this is just bad. Okay, it's not predictable what happens if we let the whatever execution we assume whatever execution to be legal. An execution to be okay must be coherent with some sequential execution. So now that we know that we cannot even increment the counter without having some kind of countermeasure, adopting some kind of countermeasure, you can think about what would happen, as an example, if thread A is inserting into a list at a given position and thread B is removing at the same position. So it would be a disaster, because you can imagine those pointers we need to adjust and to change, and those modifications should not be interleaved. So what can be done? What we can do as an example is to use a lock. Basically, a lock would is a kind of let's say every object in Java has a lock, and the lock is a kind of token with a single token that when a thread, let's say, takes the lock, it takes the token, it holds the token, no other thread is able to actually take the token. And if a thread tries to take the lock, to take the lock, and the lock is already taken, the thread is going to block. So this is basically what happens when we use the synchronized keyword on methods. It happens that when the method is executed, the thread that is executing it is going to take the lock or try to take the lock. And in this way, we can make sure that, given that there is a single lock with a single token, we can make sure that at any time, only a single thread is executing inside the method code. And as long as the thread does not release the lock, no one else is going to be able to execute that part of code. So basically, the lock is taken at the beginning of the method, and the lock is released at the end of the method. So what would it mean for us? It would mean that if you think about thread A and thread B, let's go back 1 second, check out the interleaved execution. If we take a lock, thread A takes a lock before executing its instruction. When thread B tries to take the lock before reading the counter, it would block. And given that thread B is blocked, thread A would be able to complete its instruction, write back the value to the counter, and at that point it would release the lock. And at that point, thread B would be able to execute its instruction, and the execution would be sequential. And the result of the counter would be 2. And you can see also on the lower part of the slide what can be done in the case of a counter. So instead of using a simple method as the one on the left, we can change it to be synchronized. And this would work in a multi-threaded program. Also note that as in the example of the synchronization, how to synchronize a collection, a data structure, you can see that we have been using the linked list, which is a non-thread safe data structure. We do have data structures that are already thread safe in Java. So let's sum up a bit. It is possible to use a lock on the object via the synchronized keyword, and this is what I've just explained you. Such a solution is to be adopted only for those cases where there is not an existing solution already. And this is what I was saying before. We do not have to synchronize the collections we use unless these collections are not thread safe, and most even more, instead of picking a non-thread safe data structure or collection implementation, we should check out the possible presence of an already thread safe data structure. And a possible example is atomic integer. So in Java we do have an atomic integer class as an example, which is providing methods to operate over an integer in an atomic fashion. So we would not have to we would not have the need to synchronize our counter. We should have just changed the variable type from integer to be an atomic integer. Okay, the last part of the, let's say, slide, the last 2 points are a bit more, let's say, advanced. I will not say much about this. I just want you to know that basically using a lock will block threads. And this is not always desirable. Basically, what happens is that when we have, and it gets even worse when we have a huge amount of threads. So blocking threads is wasting resources. And we can somehow adopt more advanced solutions. Namely, there exist lock-free data structures. As an example, you could check out the Traber stack on the web, and on Wikipedia I saw something to try to understand how this data structure work. Okay, I think we are done.
Yeah, okay. I just wanted to add that old Java collections that appeared in Java 1 or Java 2, these are vector, hash table, properties, and a few more. They used this synchronized approach, and because of it, modern collections outperform them. So in general, if you're thinking about what to use, hash table or hash map, vector or array list, for example, it's almost always better to use newer collections because they perform better in general situations. Okay. Yeah, I will give probably a minute or two to ask questions, and I will do a 30-second commercial break. As I hope all of you know, we have a free Java Online school that goes from like writing the main methods and up to modern frameworks and clouds and some advanced concepts like CI/CD. So if you would like, you can enroll for free on mjc.school. Okay. And what about questions? Yeah, I don't really see any. I think everything was really clear. So thanks, Luca, for these two great presentations.
Yeah,
And
nobody solved the problem with the algorithm.
No, no one wrote about it, but I read this code. Does it reverse the string?
Yeah.
Yeah, okay. So first we are pushing all the characters to the stack, and then in the reverse order we are reading and building a string out of it.
Yeah.
Yeah, and I looked up. There is no string.reverse method in Java, so if you have to do it, it's like one of the ways, maybe even a good one. Not sure there.
Yeah, this is more, let's say, example algorithm. It's probably not the best way to reverse a string. Yeah, that's for sure.
Yeah, okay. Thanks again for the presentation. And guys, see you next week on the next Light Talk.
Thank you.